So my job is to talk about a bit about physics in lenses. I'm not the I'm the IB CEO and founder of the company, and I want to tell we do a lot of optic design and production. We have a company with around 60 people, production around Munich, and we did designs and lenses for well-known companies. Did the RE65 DNAs, the Ingenieux Optimos, the primes, at least not the zooms, and we also have our own coral anamorphics, where they're shown the so-called blue lenses out there, and we have our own series of Raptor macros and stuff like that. Just to have an introduction in my person, then some slides to the company, some insights. We have an own coding area in our company. We have all the mechanic optical production in-house. And we are talking today a bit about optical aberrations. So means, why the hell is it so complicated to get a lens? And the main question is, what led me to that folies is, why do we need lenses at least? And there is some proof of concept that we don't really need lenses. We know it from the pinhole design that you can make a lens or make a picture with just a little hole. And we have prepared here an exercise for you. The biggest hole is, at least we have the open camera, and we just look at the sensor. And one guy said to me, the camera does the image and not the lens. First hand, you would laugh to that idea, but it's not. So of course the camera does the image. But the reason why you don't see anything with this high aperture is that you have a lot of aberrations, and these aberrations introduce a lot of noise on the camera, and you don't see really the image, at least. And we have here you see something? Yeah, you see it's the live image. Now we are fully open, and what we do now is we close a bit the camera hole in front and bring it down to 5 mil, 10 mil, okay. Then we see immediately, we see something of a live image. It's nothing really be useful, and we wanted to have more light. Than yesterday we were a bit too dark, we didn't see anything. Now we go down to then 5 mil, and we push a bit the ISO. So with the digital camera, you can really easily do the test by yourself. It's really, really amazing what you at least finally will see. So you get more and more structures. So the aberrations, the geometric aberrations, going down and down and down. And while we're going down with the aperture, we will see. It's a bit complicated with the ISO, always to align the ISOs on it. So probably meanwhile it could happen that we could see faces, some people sitting in the area. You see now, it's the first, I would say, 1 millimeter stop now. So you see a kind of an image, but we go further down. I give you the formula at the end, what you really need to have. Now we have the final one. Yep. So we put the final one. That is a 0.3 millimeter diameter, and it's very important that the hole is made of a ultra thin material, and the roundness of the hole must be perfect. If you can do that, you immediately see. Now we can really probably see the people, and I see that's you with the shoes here, yeah, with the face. If you would have introduced much more light, believe me, you really can take a picture. It's just a hole. So we are talking about a hole in front of a sensor. So the focal length of this hole is the distance from the hole to the sensor. Yeah. So just to let you know. So why do I? We see here on the monitor, we see it a bit better at least. Maybe you tilt it. People believe it. And you can really make very nice. We sell pinholes like this. We have it as a kind of of a gag. It's just a cap for the camera, but you immediately have something to do a shot with it. So if you do a black and white shots, it's really a kind of a new experience. Really, I loved it. So the main question was, why the hell do we need lenses? Normally we wouldn't have to have a lens, but we see when we look at the exposure and at the light, what we need doing an image like this with a hole, we need much too much light. And for a video or a movie, you know, we need minimum 24 images a second. Means you have a very short exposure time, and that means you need more light, and that means you have to gather more light on the region of the camera sensor, and at least that is the reason that we need lenses. But that is also the reason that we have to care for aberrations that lens is introducing to this optical or image giving system. Here is, by the way, the formula. Here, see the formula. It's the 2h is the diameter. It's 1.6 times square root of the wavelength, and the focal length means the distance from the hole to the camera. So just a little episode to start with. Now we're coming to the aberrations. What is the main thing I wanted to talk to you? It's rather famous. I don't know whether some of you have ever heard about it. It's called the sidal aberrations. Normally there are 5 of them, and we added some 2 more. It's the chromatic aberrations. So these 7 candidates you have to fight against if you design a lens. And it's always, we will see, it's a balancing of these aberrations to get the maximum out of your lens. If you can reduce anything to 0, you have the perfect lens, what is not existing. You always rest of aberrations, but it's just the balancing what aberration you want to stay with and what aberrations you have to solve. And we're coming to so Mr. Seidel, by the way, was an inventor, mathematician on the Munich University. So it's all, and a lot of people in the optical industry, as you might know, Mr. Abe, etc., a lot of them coming from Germany, from this area. So we're coming to the number 1, and probably the most important aberration is the spherical aberration, and what has effect what you in daily use probably will see. The spherical aberration shows you a kind of a caustic here. We have the bad rays, as we call them, means the rays that are coming in a very high aperture, in a very high entrance pupil, and they are focused closer to the lens. And the near paraxial lenses means that the rays that are nearby the optical axis have their focus far beyond. Now, the main problem on this is that if you, normally you know that if you focus the lens, you put the aperture to its maximum stop. You want to open a 1.3 or 1.4 or 1.5 to the maximum stop. Why? You have a very shallow depth, and then you can really distinctly focus. And you say, now I got it. I got this whimpers or this skin area, blah, blah, blah. And then you hope when you stop down the lens, the quality will be better. But if you have a lens that has main spherical aberration, it will not happen what you think it will happen. Because while stopping down the lens here, in this area, you image, or the energy of the rays that are coming very close around the axis is moving away from your perfect focus. And this is it's an error or mistake we call the aperture error or the stop error. And if the designer is not really critical in handling that, you always have this problem. There's a very famous lens out there from the early days. It's the Master Prime, because they're very high aperture lens. It's a fine lens. Don't want to say anything about it. It's just a good example, because the Master Prime, when you use it at 1.3, and we measured that several times, and people that know the lenses know it, that you have a 0.1 millimeter spherical aberration, a movement in focus. If you focus it by 1.3 and you go down, stop down to 5.6, the real image is moving with 1/10 of a millimeter. So in the former days with the film, it was not a real big problem. Why? The sensor of a film has a depth. And this depth is within 1/10 of a millimeter, means the areas, the color, the sensitive areas are a kind of getting the light on the right position. But with the sensors, they have a very strict plane. It is a problem. It's a much more difficult problem with the digital sensors nowadays. I guess everybody or a lot of from you will know that effect a bit. We go a bit deeper. So the spherical aberration also is not just a negative thing. By the way, it's an axial aberration. We get some off-axis aberrations then later. But this spherical aberration also is a fine-tuning utility if you know how to handle it. Because with the spherical aberration, if you know how to spot at the image area here, we are at the image area, and we see that the caustic of the rays, they're not meeting in one point perfectly because they have aberration of rest of errors. Normally they should meet in one point. They don't do that. So they are kind of have the highest energy somewhere here, and it depends where you really focus onto. If you go to the cut of A, you see here a ring of red. The red light is the one that has a far-off focus. The blue one has a closer focus. We come to that color aberration later. And then we get a focus like this. And on the far end, you have more intensity in the middle and lower intensity in the very rim of the image. And you see here more the blue line out there. So it could be interesting if you really want to have some bouquet things. Bouquet is something we are not looking at the sharp image, we are looking at the not sharp field behind and before that. That means if I know how to handle that, I can really, it's not easy, but I can really kind of design and deliver bouquets as I want them. This is it's a bit simple what I'm telling you at the moment, but I can't make it too complicated, just to give you an imagination that physically with the new software tools you could go away like this in that dimension. So the correction of the spherical aberration, because of there are normally a lens don't want to have any aberration, so the perfect lens designers or the perfect lens manufacturers. So as we did, for instance, the Optimos for Ingenieux, the Optimos are very perfect lenses, for instance. You want to get rid of all the aberrations. You want to kill that all. Not everybody wants that, but if you want that, you have some possibilities to overcome the spherical aberration, and then leads a bit to the fair way how to see the pricing in lenses. So means if you have a high aperture lens, if you really correct for all the aberrations, you will see you need more elements or just more expensive elements in it. And one of the reasons you see here, a good model for the lens or the rays is if you see it as small prisms. You have like a small prism and the refraction of the rays goes like this. And then you find out that if this surface is not a real spherical surface, it's a not spherical or an aspheric surface, then you can get rid of the spherical aberration. Means you're bending this ray much more than this ray. This has more steep angle like this way, and so you can solve this aberration and bring the focus to one single point. At one color, we come to that moment. That's the other point. So, or you take just more lenses correcting this. 2 ways at least, 3 ways at least. You don't want to have a T-stop 1.3, 1.4 or very high aperture lens, then you have less spherical aberration. The lens is cheaper. If you don't need it, don't buy it, at least. But if you want to have it, the high aperture, you have to correct for it. And if you want to have a good lens, there are more elements, more expensive elements in it, and the tolerances are much higher than before. And this is a way you should understand that cost. The next aberration is coma. Has nothing to do when you're in a hospital and lay in coma. You know you have no, you're not reacting on anything. Coma is quite simple. When you look at the image here on the right-hand side, you see a coma kind of figure on the edges of an image. This is a so-called off-axis aberration. This is an aberration that kind of rather tricky to get rid of. There's a very simple way to get rid of, but in the mix with the colors, it's not so super easy, and also it's more effort as you leave it. So this off-axis error comes because you see it in this sketch a bit. Your rays coming in on the spherical surface, and imagine you have two planes. You have the plane on the screen here, and you have the orthogonal plane that goes in there. And this plane is facing another structure of the sphere than this plane. So it's a kind of an elliptic touch of the rays on the lens that leads to the point that the rays are focused in different orientations and different distances, and then leads to the effect of a kind of a not symmetric spot. And this not symmetric spot does reduce resolution and gives you this this aberration here. One way to easily solve that problem is, where's the point? The right position of the stop. So you see here on the left-hand side, you see here the stop is after the lens, and all the rays they go the same way in than here, and all the rays going in here, and you see the so-called chief ray is the mid ray of an optical system that gives you the kind of symmetry. You have a chief ray on the image plane here, and the chief ray is the center, and you have some on the above and below, and you see it's asymmetric. If you move the stop to another point before the lens, you get a kind of rid of this bad ray here because you block it, and then you get a more spherical spot. It's of course all a bit simplified, but at least that works. So if you change the position of the spot, you can kind of play around with the coma effect. So be aware that the coma, if the coma is on axis in a projection or in your camera, you have a decentered system. All off-axis aberrations I'm telling you shouldn't be seeable or detectable when you're on the axis. It's then off-axis, it's decentered, then it's an off-axis coma again. It's a good hint to see, oh, something is wrong. Another guy that's rather complicated to explain is astigmatism. It's a bit kind of similar to the coma. You have again two planes. We have the blue rays here, maybe this plane in the screen, and this plane, the red one, also touching other areas in a spherical world. Just imagine when you come in an off-axis position, you're not really facing or touching the same area of the spherical something. That leads to the effect that you get different focals here. And the result is that a structure like this will be have an image like this. It means the tangential and sagittal focus is different. So if you look at the cross of a window, so this cross is sharp or this is sharp. You see the pumping. You see that also when you go in a projection on a projector image, and these structures are kind of pumping, then you have the astigmatism. Again, if you have this astigmatism in the very center of the image, the lens is decentered. Something's wrong. So this, the next guy, I have maybe to summarize, the one rule is there are 3 points. A perfect point in the object space should be a perfect point in the image. A perfect line in the object should be a perfect line in the image. A perfect surface should be a perfect plane surface in the image. So we talked about spots, means the point, and now we're coming to the plane, to the surface. And this is an effect you all know probably. On some lenses you want to have it. The old Petzval lenses, for instance, have a lot of curvature, field curvature. Some people like that. You see here on the right-hand side the field curvature when it's rather extreme. So it means we have not a very plain, super corrected image. But I wrote it in here. So in the artistic field, you must be cautious because my feeling is that you not always have to overcorrect the curvature, field curvature. Why? the object outside in the real world is 3D. We are not looking at a plain test target all the times, have a lens and bring it to a plain sensor. Real life is 3D. You have a depth in your field. It means if you're looking on a projected lens, don't be too critical. If the lens has field curvature, it firstly assumes that in the very mid it's sharp, but the sharpness, if you go with a paper, maybe with a leaf of paper where you go outside and you find it's also sharp in a kind of a radius, in a banded image, then it's okay out there. Because you will very seldom, besides this wall here, maybe if you take a photo of this wall, then it's a kind of a problem. But normally if you have a scenery in the wood or in the area, it's at least not so critical. And you overestimate that effect, probably. But you have maybe a good lens on the other points. So this is something you have to also to be aware of. So the field curvature is at least just a summary of all these image points, perfect points on this surface where they are in best focus at least. And you can overcome that. There's a certain rule because all, I would say that the perfect optic design is when the object is a round, is a banded curve. The sensor would be a banded surface, and then the correction would be quite easy. What we try to do is plane what is physically nonsense at least, but that's the fact. And you try to get it done here on this. But don't be too over-sensible on this. Distortion, sometimes a bit underestimated, I would say. So distortion can lead to the effect that if the distortion is in the wrong direction as the anamorphic lenses, and we saw some when you look at the projection, we saw some, they have the wrong correction in distortion because everybody would await for certain lenses having certain distortion. I take another example, not the anamorphic, I take the endoscopic world. When you have an endoscopic or macro world, you would expect the distortion to be barrel. Because this is what when you look in a hole, you would await from your feeling. You would say, this must be a barrel. If you have a distortion like this, that pincushion, you would say, yeah, something's wrong. It's really true. When you, we are used to that somehow. And be aware, if you look at the distortion on projection, it's the different sign as on your image. If you expect the distortion that is barrel on your image, in projection you should see pincushion. It's a very interesting effect when people are looking at lenses in projection and they say, yeah, it's the right distortion, but it's always the other way around on the image. It's a very critical thing. So there are, I would say, 3: barrel, pincushion, and mustache, how I call it. So this is more the distortion. That the effect could be when you have a lot of spherical elements in the system, they are not spherical, and you have a kind of a swing in your distortion. Especially the super wide lenses, they are corrected for distortion kind of. They have this effect, where you're pumping up, and the distortion is not similar over the whole field. So this is the center, this is the rim, and it's changing a lot. So it can cause a lot of unlikely effects. Yeah, this is. So there are other 2, I would say. Probably you know it or you heard about it. The one distortion we talking about is the radial distortion. That's one field. The radial distortion is at least going from the center of an image and scanning this size here. So means you always have a length. You await the length to be equal, but the length is a kind of being positive influenced, and it's getting longer than you would expect. It's a positive pincushion distortion. And there is another description on distortion. It's the TV distortion. And here you look at the long side of this line, and it's the formula being this difference, this height, divided by the full height of the image. That's called the TV distortion. You see here on the blue screen, the numbers are completely different to the radial distortion. So be careful when you compare things. They have different distortion areas in the field. So, the loved chromatic aberrations. It's really hard to also for designers to come around that. We have the chromatic aberration, we have a longitudinal, and we have a lateral chromatic aberration. So again, we take a prism as a model. This prism is separating the light, the white light, into red and blue. Just remember, the blue one has the nearest focus, the red one has the focus in the far distance. Now, if we have a model of a lens, we say it's a prism as a model. And this lens has different foci with the different wavelengths, blue, green, and red. And here are always the images of that. So what you could expect is that if you're far away from the lens, the image of the red something is bigger than the image of the blue something. Then is a kind of a sketch here, means the red, the green, and the blue have different magnification. So this different magnification means lateral color. And lateral color is always very extreme. In all systems, they are very unsymmetric. Maybe one rule to that, the best lens always is the supersymmetric system. Means on the left-hand side of the stop is the same as on the right-hand side of the stop. A typical lens design is the Gaussian lens, maybe 4, 6 lenses Gauss, double Gauss. You have that rather symmetric, and we come to that with the side aberration scale. You have the left guys do the same aberration than the right guys do, but in a different sign convention. And you kill them all to 0. So a supersymmetric system, like our pinhole, by the way, has no distortion, has no color, because there is no glass. So at least it's the perfect lens, but it has too much diffraction. We don't have diffraction. And we need light. So you see, it causes a lot of trouble to get more light, because we have to overcome all these aberrations because of that. Otherwise, it would be rather easy. So this matters a bit, of course, to the glass. If you ever seen a glass table out there from Schott or from Corning or for CDGM, the Chinese glass, you have a map of glass, and you have the refractive index from bottom to the top, and from left to right you have the dispersion, means how much is the difference between blue and red. And all this map, it's not a continuous thing. You cannot take lenses as you want, because there are just several lenses available. That makes it also rather difficult in that system. So again, a model, how to overcome that chromatic aberration. You take a glass, a flint glass, probably, one of the left-hand side with lower distortion, and combine it with a glass with higher dispersion, and then you find the right combination. Then you bring these two rays together. A model in that way. So it's the same here. You have a blue and a red. You take two different lenses with two different dispersions in a certain combination, and then you bring two wavelengths together. Bringing two wavelengths together, you always, with a singlet, you always have a color aberration, always. So to solve that, at least you have to make an achromat and kill that. If you have an achromat, two glasses, you maximize it to 2 points. Here is the image plane. This black line is your image. This is the wavelength from blue to red, and this is the focus shift at your image. And if you have 2 points where you meet the plane, mean the perfect focus, means here in red and here in the blue region, you have an achromat. If you want to have these dots are wrong here, I don't know why. So if you have a curve like this, you have 3 dots on the line, you have an apochromatic correction. So as we do our macro raptors, our apochromatic corrected, so we have 3 points to meet this area. There's more correction necessary. You have a super achromatic, like Zeiss did it with some of their apochromatic lenses. You have 5 points where you meet the image surface. At least it's never perfect one line. It's always a kind of a curve. The swingers are always kind of getting smaller. So the focus difference from the blue to the red will be smaller when the line is a kind of like a snake around this image field. And this is a very, how to say, a very mighty experience for designers to have the right glass combinations. That's really, I would say, I do it 35 years now. It's a kind of expertise. You know what glasses matching are very good and which glasses don't. And you also know, are they complicated to produce or not? And this is the experience you at least need to have a bit in that point. So now we come to an example how they could look like. This is a design I did for the big IMAX format. It's a 80 millimeter image sensor, 80. So the Alexa 65 has open gate 60 millimeter. So I just want that you realize what that means. A 1.4 f-stop is if you divide it 80 by 1.4, you come down to 60. It's a 1.0 for 60. If you see the depth of field, it's the same behavior. A 1.0 in this field, or you go deep down to the full frame, it's another 1.4 division. Then you have a 0.7 for full frame. That's similar. You could scale it down to this, guys, so that you understand a bit what that is. It's a bit big on the other side. You see, this is 80 mil. You can imagine how the size is. So here you see all the aberrations I've talked about. You always have the addition of all aberrations at least. You have the spherical astigmatism, you have the coma, all with any color combined on blue and red and green, whatever. You have a lot of aberrations. They are superimposed and come together finally. And you see then a spot here on the image field and a spot out there, and what we could immediately see, a kind of a form like a coma, like a color aberration. This color means it's greenish, it's reddish. They're not on the same place. They're kind of a bit offset in lateral. But it always depends in what size, in what dimension. It's never perfect. So that is always the dream people have. But you have to balance it, and that's the really artificial thing with lens designers, to balance that out. So, and for balancing that out, there's a good tool. If we come back to the sidles, you see on the very bottom line, in red, spherical, green coma, astigmatism, field curvature, distortion, axial and lateral color, all the aberrations. And we have all the aberrations now analyzed over the surfaces. So I have this lens here, and the surface 1 has this column aberration. Yellow is distortion. A lot of distortion is introduced by this surface. Number 2, also a lot of distortion is influenced, and it means the direction up or downward is the sign in what direction it goes. Yeah. So we have a lot of coma. So the surface 1 doesn't introduce a lot of coma, but the 2 does. And you see these aberrations now one by one. I have to jump here because number 3 is here, number 4 is here, number 5, number 6. If you come to number 6, a lot of spherical aberration. This guy here. So if I see a surface of a lot of spherical aberration, I immediately think about how can I correct that. You could probably use this surface and make a sphere to reduce this spherical aberration, because we've learned we can correct spherical aberration in bringing in another surface type to correct that. Or you need to balance it out with other lenses. So number 6 has a lot of spherical, as we see, and a lot of minus distortion. So this guy here corrects these 2 surfaces in the front. this kills the distortion that the front group did. And now you see it's how this balancing works. You have just some parameters. It's 2 radii, it's the glass, and the distance or the position where it is, I would say. But that's it, how you can play around. Yeah. And always the angle of that field. So I'm coming out from the older days. We are used to really design lenses with a lot of mostly women. They sat all like you here in rows. It were 40 to 50 women, and the left 2 lines had maybe the axial rays. The next line had the rays that are a bit higher, and the other people did the rays on the very rim of the lens. What did they do? It's just rather simple. Yeah, you take a ray, and you have some rules how this ray is banded on the surface with the refractive index. You're just calculating the angles. Angle, 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 angle. And you try to figure out where the hell is this ray coming on the image. And all these people together calculated all these rays, and hopefully they met in one point. If they didn't, you started again and changed some of the radius to align that. It was really that way in the 60s, 70s. People worked like that. So the very good thing with that is that with the super quick computers and good computers nowadays, you can kind of having multi-threads on work, because it's a symmetrical problem. If you take rays in one quarter of a lens and the other quarter, at least it's always the same. So you can have the highest machines, or the most powerful PCs, computers, always have been around in the optical design, because it's a simulation process with 100,000 millions of rays with colors and blah blah blah, and the only aim is to find the perfect spot out there. It's really interesting, at least. But there's never a perfect solution. That makes it a bit complicated. It's an open thing. I've read about that there are 3-lens system, for instance, with 3 lenses. There are around 1,700 solutions. Everything makes an image, but a kind of different. So it's never the perfect right solution. So you, as the optical designer, it's you're balancing. Do I want more distortion? Do I leave more distortion, but I'm very good in spherical? I'm very good in this and that. It's this balancing, because it's never perfect. So this is a rather good tool to analyze a system. And when you're experienced, when you do it for years, you immediately also know where the hell are the critical points. They mostly always there where you have the highest change in angle. So in a ray, when you're looking at a schedule like this, and you see when the ray its orientation is a kind of very extreme. And this normally always the most sensitive areas. And this most sensitive areas has to be compensated for when you do lenses. You need to be clear that you have finally to move to align these lenses in your final process. Because normally nothing is without any tolerance. So it means these candidates you have to align finally in your optical process. Otherwise you will never reach the design quality. You will never have zero tolerances on that. So as an experienced designer, you can immediately say, oh, this and this lens might be troublesome. So this is the way how you see the graphics out there when people want to see how the aberrations are. Lateral color here downwards in microns. It's 10 microns, maximum 10 microns here. So pixel size is 5 microns, 8 microns, whatever. And when you within this pixel sizes, you're quite good in the correction. This is the field. This is the very rim, the axis. Here you see the focal shift. Again, with our 2 points, we meet 2 points in the image. We have a focal shift of around maybe, here to the blue you see it's 100 micron, 0.1 millimeter to the very blue. By the way, there's another interesting point with the new LED projectors. Maybe you found that out also. They have much more blue light than the old tungsten projectors had. And when you look nowadays on lenses, you checked with the old cross-seal tungsten projectors against the LED projectors without any filtering, you see much more blue aberration. And that brings some people in a kind of a problem because the lenses look at least worse. But you did a lot of movies with it, you say it's okay. But the blue light really is much more difficult nowadays to design lenses in projection for the LED projectors, believe me. You will see much more a degradation of lenses if you don't have this blue light in a very mighty way. Here is the field curvature, so means the not plane surface, it's never plane, I mentioned that. Here you see the distortion in a radial manner, distortion in a TV, but it's more the broadcast field where the TV distortion is, and you can have it like where should the points be on the very rim and where they are, kind of a vector diagram. And then finally, if you have the lens ready, probably you have heard about the MTF graphic. I guess you know about, or MTF, you ever heard about it? Something you know? Okay. So this is the king size of having the overall quality of a lens. At least it's a kind of an analog system instrument like in the electronic. You have, imagine the electronic rectangular signal. A perfect signal is like this, black, white, black, white, black, white. Going through your lens with aberration, it will no more be perfect. It will a kind of lose contrast. That's the height, and with kind of lose the edges. So it will be not as good as it was when it came in. And this degradation, this behavior, you can see here. You see here the line pairs, and here this cutout of this area. You see here it's worse, and here it's better. And to see that on a line, it's like this. You have here from optical axis to the very rim. It's always symmetric. It's always axis to the rim, never the diameter. And here you have the MTF frequency. One is perfect, doesn't exist. One is that what you introduce in a lens. And then you see a 5, 10, 20, 40 line pairs a millimeter, 40 black and white pairs in 1 millimeter. That's the resolution, what you see here with this special contrast. And I can tell you when you have around 40 lines above 60, 50%, it's quite good. You have your image. 5 lines per millimeter is quite good for this tremendous big lens. This is a rather complicated mathematics behind it. By the way, we have set up a machine for measuring and adjusting all these things in our house because we finally adjust every lens with this technique. We look at any lens finally on these parameters and adjust always minimum 2 compensators to get the best balancing. Yep. For this test, we have a PCO camera from a rather good noise-free. It must be very, very noise-free sensor for this test. But at least the trick is that you look with the lens, the lens under test, to a virtual image, and we magnify it with a microscopic lens to get rid of the sensor resolution. You know, so we really magnify this intermediate image with a very good microscopic image. Then you have to calibrate it once, and then you get much less pain in the ass with the sensor resolution. But you're right, otherwise you can't resolve that. No. Because you must far beyond that what you're measuring. It's clear. So, I think we are rather far away. What I could mainly say, because then you understand a bit what pain we suffer when we design. There's a thing like local optimization. Just remember or imagine you're in the Alps, in the mountains, and you're starting with an optical design. You're starting somewhere. What you're looking for is the deepest valley. Yeah. What you're looking is the deepest valley, and to find the deepest valley, the algorithm, the stupid algorithm, would just jump around within here. He said, no, I don't want to climb that hill because I found the deepest valley. He's not aware of that there is another deeper valley when he's climbing the hill and looking down. And that's a real big problem with the algorithms in the optical design. So if you're a very experienced optic designer, you take this and put it somewhere else because you know out of experience I have to go in this region to get this design super done. And there is a newer structure for years now existing. It's called the global optimization. Means the algorithm is really forcing the system to climb over the hill and looking whether there is a deeper valley after that. And even if he found that, he's climbing another hill, whether there's another deeper valley in it. So it's a rather time-consuming ray tracing process and trying to find out regions that were better. If you're experienced, you can speed that process up, of course, enormous, because you put them in the right region. So don't start with 2 plain glasses and say, design me a 1.4 85 millimeter lens. Doesn't work, because it don't know where to go. So here you see a mapping. When your start point is here, the red area is the high level, and the green is the low level. And what area you start, that's something that did the university in Netherlands one day, and they started on just different positions, rather close together, and wanted to have a 2-lens system optimized. And these are the 4 solutions, at least they came out. What was a proof of there's never the same solution. If you put 5 designers, you give them the same task and say, do, and they all are in their rooms and do their work, they will come to a completely different solution. That's the artificial thing with designing. Okay, thank you. Thanks a lot. I have to give the place here. Thank you.